All right. So here's a problem I took out of the book, 8b-21. And we're going to do direct integration for this. The problem is asking for the slope and displacement at C. And C is the free end. So this was A. This was B. So we want the slope and displacement at C. So for conjugate beam, the first step is I need to find the moment diagram for that. So we'll start with the reactions. So I'll assume positive shear at A. It's hard to know what this shear is at the reaction because it's in the middle. So I'm just going to say I have a reaction of BY. So the first thing we want to do is find those reactions. So I will sum moments at A to find BY. So let's sum moments at A, make sure it's equal to 0. When I do that, both my forces are going to create negative moment. So I'll have 8 kilonewtons times 3 meters minus 4 kilonewtons times 9 meters. Then the moment that BY creates about A is positive, and it has a moment arm of 6 meters. So what's BY equal to?
10.
6, yeah, 10. That seems reasonable. And now we can find the shear at A by summing forces in the y direction and making sure they're in equilibrium. So with up is positive, I've got the shear at A acting up, my reaction at BY acting up, and then both these forces acting down. So minus 8 kilonewtons, minus 4 kilonewtons. So what is the shear at A? 2. Seems reasonable. Did I do that right? Yeah? If we don't get this right, we're kind of dead in the water getting started. Does that look okay? So now I can draw my shear and moment diagram. So there's my left edge and my right edge. I know something's going to happen at this force and something's going to happen here at the reaction. There's kind of my template. So I'll assume positive X, positive shear. All my units will be in kilonewtons. So starting on the left side, what is the shear at A? It's 2. There's no load, so there's no change. So I stay at 2. Then as I go from left to right, my shear changes by negative 8. So that should drop me, 2 minus 8 drops me down to 6. There's no load over the neck, so it stays there. And then I hit BY. As I go from left to right, I go up the amount BY. BY is 10, so 6 plus 10 brings me to 4. And again, there's no change, so I stay like that. So there's my shear diagram. Now let's do the moment. This is the critical one because this is the one that's going to dictate the load on the conjugate beam. So I know I'm going to start here with no moment at the pin. The change in moment over the first 3 meters is this part. That's positive. 3 times 2 is 6. It's constant positive, so I have a constant positive slope. The change over the next 3 meters is negative. That'll be 6 times 3 is 18. 6 minus 18 is minus 12. Right? And then the last 8 feet will be positive. 3 times 4 is positive 12. And brings us back to 0. So that's a nice moment diagram, huh? Now, normally we don't worry about this, but since the moment diagram is going to be applied as load to the conjugate beam, right, we probably need to find this little value right here, this distance. I'll call it x1. What would that be? Well, remember, the change in moment is equal to the area under the shear diagram, right? Which is this little chunk right here. And that's minus 6 times x1. And, of course, the change is minus 6. So the change in moment is equal to minus 6. The area under the shear diagram is equal to minus 6x1. And, of course, those two things are equal. So what's x1 equal to? 1. So this section would be 1 meter, this section would be 2 meters. So we have all the distances we need. So what looks like a fairly innocent problem is now developing into kind of an interesting looking moment diagram. Right? So we now have 1, 2, 3, 4 triangular loads. And we haven't even gotten started yet. But now we are. So what's the conjugate beam of this thing look like? So, a external pin is a what in the conjugate beam? External pin. An internal roller in the real beam is what in the conjugate beam? Hinge. And a free end becomes fixed. So we end up with something that looks like this. Pin, hinge, fixed. And on that, we drop this guy. This is going to be exciting. I can see you guys are already really ready for this. You ready? Here we go. So, it looks something like so I just took the moment diagram and I transferred it over. So that's the first 3 meters, and there's the transition into the last 3 meters. And of course, this would be 6 kilonewton meters divided by EI. And this would be minus 12, or just 12 kilonewton meters divided by EI. Positive moment is positive load, and positive load is up. Negative moment equates to negative load, and negative load is down. So this would be 3, 1, 2, and 3 for the distances. Wow. Are you super excited about this problem? I am. So we want to find the slope and displacement at C, which is here. So in this beam, in the conjugate beam, slope is what? Shear. So there's positive shear at C. And the displacement at C in the real beam is what in the conjugate beam? moment, and there's positive moment. So all I have to do is find those reactions, and I'm done. See? It's easy. How do I do that? Well, how many reactions here to fixed connection?
2.
3. How many here to pin? 2. I can't draw one free body, can I? That would be bad. So I'm going to have to break this apart. Oh, an audible oh. I think we're going to run out of time. But I'll go ahead and set it up. So if I broke the first free body apart, what would I get? So I'm just going to go ahead and say, hey, there's positive shear at A. We won't worry about the X components. And then, hey, here's the positive shear at B.
Why do you have to break the S up?
I can't solve for it.
Wouldn't you just
I wouldn't have enough equations.
moment at C to get A, and then...
You can't. Because there'd be one equation and two unknowns. You'd have the moment and the shear.
You said, are you cutting it at B?
I'm taking it apart here at B. So let me draw what's happening at B.
And can we just work the other side?
You can, because you don't know what's happening at B. You got to find B to pass it to the other side to then solve it. Boy, I sense resistance to this problem. So that's what's happening on this side. What's happening on the other side? Oh, I do that way too big. So all I'm missing on that side would be this load. See that? So if I can find this guy, if I sum moments at A and find B, then I pass B over here, then I can sum moments at C and find the moment, sum forces in the Y and find C. But you can see it's going to be a little troublesome to do all that. You guys see that? So this is 3 meters, this is 1 meter, this is 2 meters, this side is 3. So it's going to be a lot to keep track of. So that's, again, even though this is kind of simple to apply, straightforward to apply, you can see it's going to be a lot of accounting to do. Because when I sum moments about A, I'm going to have this triangular load to deal with, and then this little piece to deal with, and then this piece to deal with. So I'm going to get 3 loads and 3 distances just to find the shear at B. Then I pass it over here. I've just got 1 triangular load here to do. This is going to be some work. So what I'm going to do is I'll stop here. That's a lot of time. I'm sure you appreciate that. I'll finish this in my office sometime today, and I'll publish it online for you to see.
So you said you would still need to do that first part you cut off to get BB, right?
You got to do this part. Find BB. Pass it over here, and then you can sum moments to find the moment, and you can sum forces to find the shear.
Okay. And then you're going to use that second part for the rest of your problem?
I'm going to solve this problem first, BB.
Yeah.
Put BB here. Solve that problem.
Okay.
You wanted to see one with positive and negative, right?
Say what?
You said you wanted to see one with positive and negative, right?
Yeah.